A thermometer circuit design with operational amplifier and bipolar junction transistor is discussed in this example. The circuit is implemented with one op amp or operational amplifier and 6 bipolar junction transistor, in this case P-type BJT, but a variant of this circuit can be implemented with N-type transistors as well. We want to see how the circuit is working, and then with a quick analysis we want to show that the output voltage, assuming proper selection of the value of resistors, is going to be proportional to the junction temperature of transistors in Kelvin. So let's see how it works. Let's make the assumption that op amp is properly biased, so the supply voltage is, let's say, plus 10 volt and minus 10 volts or plus minus 5 are there. You can see that the output voltage via for the op amp via this resistor R2 is connected to input inverting or negative terminal, indicating proper negative feedback. So op amp properly biased, and with negative feedback, therefore op amp operating in linear region, and because of that I can say that virtual short is valid. So op amp in linear region and virtual short is valid for the op amp, which means the voltage at the positive input terminal is equal to the voltage at the negative input terminal for the op amp. Let's keep this as equation number 1. Now let's go back to transistors. We have T1, bipolar junction transistor T1, we have T2, we have T3 and T4. These 4 transistors are forming a current meter. Basically this one is setting the reference current T1 and resistor R. So this bipolar junction transistor T1 and resistor R effectively setting the reference current IR, which is easy to calculate because we can say that from, say, V supply, that is here, so Vs could be 10 volt for example, and we have between emitter base voltage drop for T1 we have about 0.7 volt. So the collector of this transistor, given the collector connected to base, is going to be at Vs minus 0.7, and then you can see that the other side of resistor is just grounded. So basically we can find the voltage, we have the voltage drop across R, and we can find IR. So this reference current IR is simply Vs minus 0.7 divided by R. So we can set the reference current by proper selection of the Vs and R. Now what happens is transistors T2 and T3 and T4, because their emitter base are copy-pasting the emitter base of T1, they have to copy-paste the current, assuming all these transistors are matched transistors, so they are on the same substrate with the same junction and temperature or thermal properties. So with that in mind, so basically what I'm trying to say is this is IR, this is IR, this is IR as well. Now we have, assuming that these transistors are, let's say, low current transistors, we can assume that the current gain or beta for these transistors, or HFE, IC over IB, I collector over I base, is pretty large, much larger than 1, like 200, 100, above 100. So with that in mind, we can roughly make the assumption that the emitter current for each of these transistors is the same as the collector current. So these are IR as well. That's what I'm trying to say. Now here we have the sum of these two IR flowing, so 2 times IR flowing down and become the current of collector emitter for transistor T5. So let's refer to this one as T5. Now we can see that only one IR is going down and getting to the emitter of transistor T6. Reason we are neglecting the connection via R1 to the op amp is because we need to have a proper selection of R1 and R2 so that they are large enough that the current flowing through R1 resistors would be negligible compared to IR. So I'm going to make the assumption that R1, for example, is 15 kilo ohm. That's a good choice. And I'm going to make the assumption that, and the reason I'll present that R2 or resistor R2 is 250K and 250 kilo ohm here as well. So what happens is, since for ideal op amp that is in linear region, the input impedance is effectively infinite, there is no current flowing through the input of op amp, and effectively R1 and R2 are in series. And you can see it's a pretty sizable resistor. R1 plus R2 in series is, with these choices, is 15K plus 250K, which is 265 kilo ohm, which is very large, and we can therefore roughly say that this current going through this branch toward R1 is approximately practically zero compared to IR. It's not zero, but compared to IR is negligible. So I'm going to write it much less than IR. The same thing here. So this current is much less than IR. So therefore we can neglect that the effect of this current with respect to this node and assume that IR keeps going down and 2IR keeps going down as well after this node to here. So this one is also 2IR. Okay, so what is the benefit of this analysis? The benefit is now I can use the Shockley p-n junction equation, so the famous Shockley p-n junction current voltage equation, so IV equation, that says for, let's say, emitter base p-n junction of a p-type transistor, we can write that the current of, let's say, for transistor T5, I can write, so for T5, I can write the current that is going through, let's say, the emitter, which is 2 times IR, so I5, which is 2 times IR, is equal to the saturation current of the p-n junction times e to the power voltage of emitter base, the p-n junction voltage, for transistor 5 divide by, for transistor 5 divide by eta ideality factor of transistor times VT thermal voltage. Eta depends on the type of p-n junction. For silicon p-n junction is roughly 1, but in general it's a number between 1 and 2. So we make the assumption eta is 1. And then thermal voltage, or VT, is just the well-known K over Q times T. T is the junction temperature for transistor T5 and in Kelvin, so in Kelvin, and then K is the Boltzmann constant, so K is Boltzmann constant, and the value of that is roughly 1.606 in that ballpark times 10 to the power minus 23, and the Q, or electron charge, is 1.9, roughly 10 to the power minus 19 coulomb. So we have those numbers, and therefore what we can say is we can just keep this as equation 1 for the time being. So let me write it this way. This is equation 2. This is equation 2. I can write the Shockley p-n junction equation for also transistor T6, this one as well. I know that the current is just IR, just 1 IR. So I expect that since the current is for transistor T6, since I6 is smaller than half of I5, obviously, because I'm saying I6 is now just IR instead of 2 IR. So I expect VBE6 to be less than VBE5. So given that the base for both transistors is grounded, the emitter of 6 should be less than the emitter of 5. So I'm going to say this is again the saturation current, e to the power VBE6 divided by eta VT. Now it's very important to make sure that these two transistors are matched, so they are on the same substrate, same package, they are copy-paste of each other, and they benefit from exact same thermal junction properties, and therefore IS is assumed to be the same for both of these transistors. Otherwise we will have a problem. So let's name this as equation number 3. Okay, obviously I6 is half of I5, so I can just say it this way: I6, or I5, is simply 2 times I6, which means, as we saw in these two equations, so basically conclusion from 2 and 3, and therefore substituting for these IS for I5 from here, IS e to the VBE 5 divided by VT, I'm just setting eta equal to 1 as I said, and then 2 times IS e to the VBE 6 divided by VT. Now IS cancels out from both sides. This is important. IS is very exponentially dependent on temperature, so we want to get rid of it, and that requires the matching of these two transistors. So now after that I can take a log from both sides of this equation. So if I do that, I can say ln of this is just VBE 5 divide by Vt, and then on the other side I have 2 times this guy. So take a log of that, and it's going to give us ln2 plus, and the natural logarithm of this one is going to be, natural log of that one is going to give us VBE6 divided by Vt. So in summary, what we are going to get from this is VBE5 minus VBE6 is equal to Vt, which is Kt over Q. So I'm going to write it ln2 K over Q here times temperature. Okay, so this is equation number 4 that is important to me. Okay, so how are we going to use this? Now the rest of the process is just dealing with the op amp stage. So dealing with op amp stage that involve both non-inverting amplification and inverting amplification here. So the easiest way to do is, because of virtual short, going back to equation 1, I'm going to quickly compute the voltage at the positive or non-inverting input terminal here as V positive. And then I am going to say that because of virtual short, the voltage at the negative or inverting terminal should match that. So as mentioned here, V positive should be equal to V negative. So let's do that. There is this R1 and R2 are simply in series because, as I said, there is nothing flowing through the input terminal of ideal op amp because of effectively infinite impedance. So what I can say is Vp, or voltage at the positive non-inverting terminal of op amp, is equal to simply a voltage division between R1 and R2, R1 plus R2 times this node voltage. This node voltage is simply voltage of emitter 5, which is the voltage of basically emitter base 5, because base is just simply grounded. So times VEB 5. Okay. So what else I can do? Well, this Vp should be equal to Vn because of virtual short. So I'm going to say is equal to Vn as well because of equation 1 here, which means because of virtual short. Okay, so what's the benefit of this? The benefit of this is now I can just simply write the relationship between Vout, Vn, and voltage at this node as simply a voltage division between R2 and R1, because again no current can go through the input negative terminal of ideal op amp because of infinite impedance. So effectively it just R2 and R1 again in series. So what I can say is like this: this current is equal, so let's say I out is equal to simply, or IF, doesn't matter. So this current, I say, let's refer to it as just I out, is the same as this current, I out, and therefore I can compute that. I can say the voltage at this node is the voltage at emitter of transistor T6, or basically VEB6, because the base is grounded, and therefore I can say the I out is equal to, as you can see, is equal to VEB6, so, or let's say Vn minus VEB6 divided by the R1. So we have the two voltage across R1. The plus minus voltage drop across R1 is Vn minus VEB6, and this should be equal to also Vout minus VEB6 series of R1 and R2. So equal to Vout minus VEB6 divided by R1 plus R2. Okay, so what I'm going to do now is I'm going to just write it this way: Vn minus VEB6 equal to R1 over R1 plus R2 times Vout minus VEB6. Okay, and now we can substitute the let's say this is equation 5. We can use equation 5 to substitute for Vn with this value. So that's the final step, and we are done. So what I'm going to do is I'm going to use equation 5. Equation 5. This is effectively a difference amplifier. So we have a difference amplifier over there, and I'm going to show it without making any assumption or any memorization of any formula. So Vn is this one, and I'm going to substitute it for Vn here. So we're going to get R2 over R1 plus R2 times VEB 5, and then we have minus VEB 6, and we can then multiply, let's do it step by step, equal to R1 plus R2 Vout minus VEB 6. Okay, so as the final step, what I'm going to do is let's multiply both sides with R1 plus R2 so that we get rid of the denominator, and we end up with R2 VEB 5 minus R1 plus R2 VEB 6 equal to R1 Vout minus R1 VEB 6. Okay, so what's the benefit of this? You can see that we have minus R1 VEB 6 on the left side of the equation. So I can cancel that out with this R1 VEB 6, and what remains after all of these things will be this outcome. So we have R2 VEB 5 minus R2 VEB 6. So R2 VEB 5 minus VEB 6 equal to R1 Vout. So we are almost done. Therefore, Vout is simply R2 over R1 VEB 5 minus VEB 6, but then I can substitute that using equation 4, because in equation 4 I found that VEB 5 minus VEB 6 is equal to ln of 2 and then times k divided by q times t. So I'm going to substitute that using equation 4, substituting these guys, the difference of the two voltages, and I get ln 2. So I get, let me put it this way, k over q, and then ln 2, and then the whole thing times t. That's exactly what I wanted to find. So we found this important equation that the output voltage of this circuit, the way it's implemented, is proportional to the ratio of the two resistors R2 specifically divided by R1, and or these are the same thing, R2 R1, and then times the Boltzmann constant divided by electron charge Q, and times the ln of 2, and then temperature in degree Kelvin. That's the junction temperature for the T5, T6 transistors. So if we properly select the value of resistors like R2 250K, R1 15 kilo ohm, then we end up with 250K divided by 15 kilo ohm, and then times, of course, the Boltzmann constant and electron charge, so K over Q, ln 2. This value roughly becomes on the order of 1 milli. So it becomes effectively 1 millivolt per, let's say, degree C or Kelvin. So times temperature. So what is it saying? With this proper selection, what happens is every 1 degree increase in temperature here, so every 1 degree increase in temperature will result in the voltage Vout of this circuit increasing by 1 millivolt. So let's say 10 degree junction temperature increase results in 10 millivolt increase in output voltage of this circuit. So we have effectively constructed a thermometer that output voltage is linearly proportional to the junction temperature of the transistors. So if you're targeting measuring a temperature, we need to just make sure that the junction temperature of transistor is properly resembling that temperature. I hope that this example is helpful in terms of showing how a simple thermometer can be designed, sort of a basic thermometer with op amp and bipolar junction transistor, what assumptions we need to consider in terms of the selection of components like R1 and R2, and also a reminder of Shockley-Pinion junction I-weak equation that we have used in this equation, and also the assumption about the matching transistors. I hope this is helpful. Thanks for watching.